Hello and welcome to my new channel of basic engineering. Today we are going to start with an introduction of vectors. Vectors are very important objects in engineering that we will be using later in the course to represent forces, to represent moments, couples, and many like uh, characteristics that we will need in order to analyze, any what we refer to as a rigid body. We'll talk about all of these in the course, but in the beginning, we want to see what is the difference, or what are vectors first. In real life, you will see that we have quantities that we call scalars, and the word scalars comes from a scale. You scale it up or down. So when I say, for example, 1 meter or 1 foot, I can scale it up and make it two or five or 10, or I can scale it down and make it one half or a quarter. So any scalar quantity like length, like area, like volume, like temperature, like density, all what you need to describe it is a magnitude and a unit. So I can say 5 feet, or I can say 40 kilometers per hour. All of these are scalar quantities. But there is another family of units or objects that we call vectors. And vectors here meaning not only they have a magnitude and a unit, but they also have a direction. Like forces. Let's assume I have an object like this calculator, and I apply a force on it in this direction. You see how it moves? If I apply the same force from the other direction, it moves in an opposite way. If I push it in this, it moves to the left. Here it moves to the right. Here it doesn't move at all. If I have a box standing on the floor and I push it from down, maybe it slide. If I push it from up, it will top over and fall down. So that's why these quantities like force, like what we are going to talk about as torque, these are quantities that their direction is very important because it will tell me what would happen to the body. Apply it in one direction or another direction. So now we have scalars that, okay, they are good, but more important, we have the vectors. So let's see how we are going to deal with vectors in any engineering course. Of course, also in mathematics, you take a lot of vectors. So vectors can be in any dimension. We will start in 2 dimensions. So let's say I have my XY coordinates here. So here is my X, here is my Y. And usually what I used to tell my students in courses like that is that think of the vector city as a city that only has horizontal and vertical roads. So, for example, if you want to move from the origin, which is 0, 0, to a point that is, let's say, 4 and 3, you can either move 4 units along the x in this horizontal road, and then 3 in the vertical, or 3 in the vertical, then 4 in the horizontal, or 1 to the right, 1 up, 3 down, 2. You can do a lot of ways. For example, you're going from home to school. You can either go in this street and then that, or you may go to visit a friend, then you go eat something, then you go to school. So we have infinite number of ways to go from this point to that point. But from the point of view of vectors, I really don't care how you came here. So as a professor in college, I don't care if you came directly from school or you visited somebody or you went to grab a bite. The idea is you ended up here. So we call that vector. Going from the origin to this point, we are going to call that your displacement. So vector, if we call it O because that's the origin and that's A, I'm going to say OA with an arrow on the top. So to represent that that's a vector quantity is equivalent to your displacement. And any route that you take, no matter how complicated it is, as long as you start here and you end up there, all these displacements are equal. Okay? Now, so that's an easy representation. But then you told me you can only go horizontal and vertical. Why are you drawing that? Now, I'm drawing that to say what is the end result of your journey? Okay? Now, in order to introduce math, people thought, you know what? I'm going to say, didn't you move 4 units to the right, then units up? This is 4, this is 3. So now, in order to represent my vector, and I'm going to call it, instead of calling it OA, I'm going to call it V. Vector V here, I want to explain to you in a mathematical way. Instead of saying, well, I went to the east 4 kilometers and then I moved north 3 kilometers, it's much easier to give a name to every unit along the x and every unit along the y. So I'm going to say if this is 4 unit vector, this is also a vector. I'm going to call it v sub x, right? And I'm going to call that v sub y. So you can see along the x, along the y. If I divide that into 4 equal pieces, doesn't each one would be a unit? Like you say, oh, I traveled for 80 miles. So every mile is a unit and you did 80 of them. Exactly the same. Here they were, here is 1 unit along the positive x-axis and I did 4 of them. For simplicity, instead of saying east and west and northeast, no, we are going to call a unit vector along the positive x-axis I, the letter I. And a unit vector along the positive y-axis, we're going to call it J. And I use the caret to represent a unit vector. Okay, so instead of an arrow, I use a caret so we can see that these are vectors, but they are small vectors. So I'm going to tell you, move 4i meaning I'm going to move 4 units along the positive x-axis or eastward, and then move 3j. So this vector v now can easily be represented in math as 4i plus 3j, or 3j plus 4i. It's the same thing as we said. Or I plus j plus I plus j plus I plus j plus I. 4i's and 3j's. I don't care, as we said. Now, the next step is to say, okay, that's a vector, but I don't know how much did I travel? What is my total displacement? And likewise, can you give me a unit vector along v, like you give me a unit vector along vx and you called it I, and a unit vector along vy, you called it I. Can you divide this distance by how many units are here and tell me what is this unit? I'm going to call it E sub v, meaning a unit vector along the along the v vector. Do you see the idea? So now, instead of calling that a vector, I'm going to say, no, this is the magnitude of the vector, and this is its direction. And if these were like in miles, I'm going to put them between parentheses and write miles, or km for kilometer, or centimeter, or whatever, or Newton if it's a force. So these are the units. But as we said, a scalar is a magnitude or a scale and a unit. The vector is a magnitude and a direction and a unit. Forget about the unit for now because it can be anything. But now we have magnitude and direction. How can I find the magnitude of V and how can I find the direction of V? From now on, I'm going to, instead of saying the vector is a magnitude and a direction, I'm going to say the vector would be represented as a magnitude which we refer to as the norm of the vector, meaning its magnitude, times a direction. And the direction here is a unit vector along V. Unit vector along V. Well, wait a second. That's exactly here. When I refer to V sub x as 4 times I, a unit 4 and a direction I, plus 3j. But how can I combine them into just one? Because these are two. 4 times I plus 3 times j. What is the magnitude of OA? 99%, if not all of you already know that we use Pythagoras to help us with that, right? We can say that V equals V sub x square plus V sub y square, meaning the magnitude of V sub x. When I don't write, usually we write them between two pipes as a magnitude. So I say the magnitude of V, I would write it like that. But to simplify things, if I write it without the hat, so I want the magnitude of V, it's the square root of the magnitude of V sub x squared plus V sub y squared. In this case, it's the square root of 4 squared. And notice I used 4 and 3 because all of you know how to apply the Pythagorean theorem here. It's the square root of 16 plus 9. It's the square root of 25. It is 5. So the magnitude here is 5. If this is the vector and that's the magnitude, how do I find the direction? Many students have trouble in the beginning and then they say, oh, of course, in algebra, if I tell you V equals M times D, so how do you find D? Don't you divide both sides by the magnitude? Exactly, that's what we are going to do here. So we are going to say the direction, which is E sub V. That's, remember we said the direction we are going, which is this guy. One of these fifths. So if I divide this distance into 5 equal units, each one of them would be what? Would be what? It would be the vector itself, which is 4i plus 3j, divided by the magnitude, which we found to be 5. So you can write it as 4/5 I plus 3/5 j, or you can call it 0.8 I plus 0.6 j. One more thing. We know that that's a unit vector, meaning if you take the magnitude of that, you would take the square root of 16 over 25 plus 9 over 25, which is 25 over 25, which is 1. You don't need to check that. We already know that. But what are these 4/5 and 3/5? I know that the whole thing is a unit, but what are these two? Go back to trig. You will find so nicely that this guy is the cosine of the angle that the vector makes with the x-axis. This is theta x. And 3/5 is the sine of this angle or the cosine of that angle, which you are going to call theta sub y. Remember the word, do you know what's the meaning of cosine? Where does the nomenclature came from? Tell you that in a second. This is sine. I'm sorry, cosine. I was going to say sine theta x, but we usually say cosine theta y. So these are referred to as the directional cosines. So I ask you a question. Where does the term cosine came from? Well, we mentioned that the cosine, well, first of all, we said the sine of an angle is opposite over hypotenuse, right? And what is the cosine? Well, the cosine is equivalent to sine of complementary angle, complement. What is the complement of this angle? If this is 90, then the complement is that. And by basic geometry, these two lines are parallel because both of them are, this line is parallel to the y-axis. So these two angles are what? I'm waiting for you to say. Hmm. Alternate internal. So they have to be equal. So this angle is theta sub y. So if I ask you, what is the sine of theta sub y? You say it's opposite over hypotenuse. Oh, the opposite of that is the adjacent of that. And that's why we say it's the sine of the complementary angle of x. So cosine is the sine of the complement. We know that. And here we refer to that as the directional cosine. Later, in the next time when we go to 3D or even ND, even if you cannot visualize it, but if you go to n directions, you will find that the cosine square theta x plus cosine square theta y plus cosine square theta z plus equals 1. That's a very universal law of cosines. You learn that in trig. I hear somebody say, no, we learned sine square plus cosine square equals 1. I say, yeah, that's a special case of what we are saying. Meaning, if a line makes an angle theta x with the x-axis, theta y with the y-axis, theta sub z with the z-axis, and you square the cosines and add them up, you will get 1. So why do we say sine square? Basically, what we are saying is that cosine square theta x plus cosine square theta y equals 1. The angle that it makes with the x, the angle that it makes with the y. But then cosine theta y is the same as sine theta x, and that's why we refer to that usually in 2D as an identity in trig, which is sine square theta plus cosine square theta equals 1. And now we don't need to say x and y because it's just one angle. So we say sine square theta. But generally speaking, that's a special case in 2D in a universal law that no matter how dimensions you have, if you have a line in hyperspace that makes angles with these numerous axes, and you take the angle between this line in hyperspace and all the axes, find their cosines, square them, add them up, you will get 1. Notice that here, theta sub z is 90 degrees because the z-axis is perpendicular. So we say cosine theta square x plus cosine square y plus cosine square theta sub z equals 1. Cosine theta sub z is 90 degrees, pi over 2, and cosine square pi over 2 is 0. So we are saying cosine square theta sub x plus cosine square theta sub y plus 0 equals 1. You can generalize it like that. Now I'm going to give you two cases, and before that I'm going to show you something else, but two cases that we will use to represent vectors, be it force, be it just a regular vector or anything. First of all, we say that we drew the vector from here, right? From 0 to 4, 3. Right? So let's draw one and say this is, for example, 3, 3, whatever. And that's 0, 0. If I go from -1, 2, and I draw a line parallel to V with the same length, notice the 3 is more than the 0, so the 2 is more than the -1. The 3 is more than the 0, so the 5 is more than the 2. If these two are equal, then, and we call that W, then V equals W. They don't have to be in the same like location. I can slide a vector and move it parallel to itself without changing it. And we call that a free vector, meaning you are free to place it wherever you want. Later, we learn that forces are not free vectors. Like I told you, if I have a box sitting here and I push it from down and then move it parallel to itself and move it from up, and this box is very tall and slender, it would fall down in the second case, while it may slide on the floor in the first case. So some vectors are not free vectors, but some are, like couples. You can place them anywhere you want. Again, this is too soon for that, but that's what we are going to learn later. So that's the first thing you can do. If you know that the vector and all the vectors we are going to deal with in the beginning of this course will be free vectors, you can move them, you can slide them, as long as you don't change their magnitude and you don't change. So here the magnitude is 3 root 2, right? If this is 3 and that's 3, then this would be square root of 18 or 3 root 2. And that one also is 3 root 2. If I want to represent it, I'm going to say 2 minus negative 1i plus 5 minus 2j. So it's 3i plus 3j. Okay? Now, what if I have a vector like that and I say it makes an angle of 40 degrees with the horizontal, and its magnitude is 100, let's say 100 Newton, whatever. And then I have another vector, but this vector instead, it's passing, it has a magnitude, let's say, of 52 pounds, and it has a slope of 5 to 12. How do I represent these two? So let's call that V sub 1 and call that V sub 2. And they are free vectors, so they can be here or they can be there or whatever. If you know that, if you know the angle the vector makes with the horizontal, meaning it means that you also know the vector, the angle that it makes with the vertical, right? Because they are complementary angle. So we can say, you can represent V1 as 100 times cosine 40 degrees I, notice we have to write the direction, that's the x, plus sine 40 degrees I, or if you prefer to use the directional cosine, then you say plus cosine 40j. Both are fine with me, it doesn't matter. Newton. Oh, magnitude, direction. That's a unit vector. Why? Because its magnitude is the square root of cosine square 40 plus sine square 40, which is 1, square root of 1 is 1. But sometimes you will be given the direction as a slope like that, an x and a y, and you say, okay, how do I represent it? Notice that this is the hypotenuse. The x is 5 or negative 5 because it's to the left. If you move from this point to that point, if you are moving negative along the x, positive along the y. So use Pythagoras. You have a triangle. This is 5, this is 12, and this is the hypotenuse. So you say the hypotenuse square equals 5 square plus 12 square equals 25 plus 144 equals 169. So h equals root of 169 or 13. So that's 13. You don't need to find the angle. I've seen many students say, okay, let me use the calculator and find what's the angle whose tangent is 12 over 5 or cosine is 513 or negative 513. No, you don't need to do any of that. All what you have to do that this vector is 52 times negative 5, because it's going to the left, over 13i, plus, because it's going up, 12 over 13j pound. If you want to write it not as a magnitude times direction, but as a vector, like we wrote this for I plus 3j without a magnitude and a vector, it's just multiply. 52 over 13 is 4. So it's negative 20i plus 48j pound. And that's it. I think I will stop here. You will see also that if I want to add these two vectors, of course I can't add them because one is in Newton, the other is in pound, but let's assume this was a pound. I can add them very easy. I'm going to add the i's together, the j's together, and I will end up with a new vector. So I use my calculator and see what is 100 cosine 40, subtract 20 from that. What is 100 sine 40, and add 48 to that. I will get the sum of these two vectors, or the difference, or twice the first plus the second, or whatever you want. So any linear combination is very easily done. I think I will stop here so I don't make it a very long video. And then next time we'll take it one step further and move to the 3D case and see how we are going to deal with vectors and how do we represent them. Thank you very much for your time. Hope to see you soon. Have a nice day.